Okay, now we're going to continue with problem 11. You can see this is a problem concerning double angle formulas. So we're given tangent of theta equals -3/4, and that theta is in quadrant 2. And we're asked to find these double angles. The formula for the sine of 2 theta is 2 sine theta cosine theta. What I'm going to do is, like we've done many times before, I'm going to take this trig function and create a right triangle. Maybe I'll do it down here. And based upon this right triangle, then we can determine all the trig functions we need to plug into these formulas. So tangent of theta, tangent's TOA, right? So opposite over adjacent. So opposite would be 3, adjacent's 4. Pythagorean formula would tell us this is a 3, 4, 5 triangle. Just so I don't forget, we were told this is in quadrant 2. So now I can go back up here to this formula. The sine of theta for my triangle sine is opposite over hypotenuse, which is 3/5, and in quadrant 2 the sine is positive. Now I need to multiply by the cosine, so ca adjacent over hypotenuse. Now when quadrant 2 the cosine's negative. So now 2 times 3 times -4 is -24. So the answer for the sine of 2 theta is -24 over 25. Now the cosine of 2 theta, if you look at the formula sheet, you have 3 choices. Doesn't really matter which one we choose. So I'll just go ahead and I'll just say cosine of 2u. I'll just use the first formula. Cosine squared theta minus sine squared of theta. Cosine of theta, once again, is -4/5. I'm going to square that. I'm going to subtract sine squared of theta, so it's 3/5 squared. 16 over 25 minus 9 over 25. 7 over 25. Now for the tangent 2 theta, you could use the formula, but actually, in my opinion, it's much simpler to remember that tangent can be rewritten as a sine over the cosine. So the tangent 2 theta equals sine of 2 theta cosine 2 theta. I just calculated each one of those. The sine of 2 theta was -24 over 25. Cosine of 2 theta was 7 over 25. This is a complex fraction. I can write down the answer, but just in case you've forgotten, the way you work it mathematically is you take the top fraction, you multiply it by the reciprocal of the bottom fraction. You see these 25s cancel out, and you're left with the tangent of 2 theta being equal to -24 over 7. Double angle formula is pretty straightforward. Number 12, similar kind of problem, except now they're wanting us to determine half angles. So with half angle problems, there's a extra step from what we just did. First of all, let's go ahead, just say this. It's interesting, all the formulas for half angles, all we need to know is the cosine, because all the formulas only require the cosine. But we're given the tangent of theta. So to find the cosine, once again, I'll go down here, and I'm going to create a right triangle based upon tangent of theta is 8/15. So TOA, opposite over adjacent. So I didn't bring my calculator, but I believe 15 squared is 225. Plus 64 and I believe square root of 289 is 17. Let me just confirm that since I didn't bring my calculator. It's 49, 7. This is old-fashioned multiplication. Yep, 289. And this is in now quadrant 3. Really, all I need is the cosine, so let's just go ahead and figure it out now. So ka, it's going to be negative. So now we're going to see, I'm going to write down the formula for the sine of theta over 2. Looks pretty messy, plus or minus square root of 1 minus cosine theta. Now, the plus or minus doesn't mean there's two answers. The answers are going to either be positive or negative. And now I'm going to go take a minute and figure out whether the sign should be positive or negative. I need to figure out which quadrant the half angle is in. Now, I know theta is in quadrant 3. If you think about the unit circle, here's quadrant 3. In degrees, it's 180 to 270. So I can go up here and I can say, I can write this double-sided inequality. Theta in quadrant 3 means that it has to be between 180 degrees and 270 degrees. If I want to know about the half angle, I just divide all three parts of this by 2, and that tells me where the half angle is. So 270 divided by 2 is 135, 180 divided by 2 is 90. So the half angle is between 90 and 135. Well, 90 is right here. 135 is right here, so obviously the half angle is in quadrant 2. So based upon that, if I'm looking for the sine of the half angle, I know in quadrant 2 the sine is a positive result. So I know my answers are going to be positive. So now I'll simply plug in the cosine of theta equals negative 15/17 into this. Now this can get sort of messy. So the sine of theta over 2 is going to be 1 minus a negative 15/17 divided by 2. I need to simplify this. First thing you realize is when you subtract a negative, it's the same thing as adding. So I have 1 plus 15/17. Just in case you forget how we do this, I need to get a common denominator. So 1 becomes 17/17 plus 15, so it's going to be 32/17. So 32/17 divided by 2, if I simplify this, the 2 gets multiplied by the 17. If you divide top and bottom by 2, you get square root of 16, and now square root of 16 is 4. Now, in the world of trigonometry, it's no problem leaving the square root in the denominator. So the answer should be 4 over square root of 17. Let me check it real quick. And that is the correct answer. Now the cosine, the formula looks almost the same as the sine, except one difference. Instead of subtracting, we add 1 plus the cosine. Now let's look in quadrant 2, since the half angle is in quadrant 2, what is the cosine of quadrant 2? In quadrant 2, the cosine is negative, so now I know this answer is going to be a negative. So once again, I plug in negative 15 over 17 into the cosine here. So 1 plus, or I could just write 1 minus 15 over 17. So once again, to simplify this, 1 minus 15 over 17 is the same as 17 over 17 minus 15 over 17, which is 2 over 17 over 2. I multiply the 2 times the 17. Can divide top and the bottom by 2. Now the square root of 1 is just 1, so I should be able to simplify this and come up with negative 1 over square root of 17. Now just like for the double angle problems, the tangent of the half angle is a very messy formula. But since I already know the sine and the cosine, I'll just plug those in. So the sine is 4 over square root of 17. The cosine is negative 1 over the square root of 17. If you simplify this, you'll eventually end up with minus 4. So there we go, half or double angle and half angle problems. Now the last section we covered in this chapter was on inverse trig functions. Let me just start working these problems out, and then as I work them out, I'll remind you of the key things to remember. So when you see an inverse trig function, I always tell myself an inverse trig function is going to end up being an angle. So I ask myself the question, what's the angle where the sine is 0? But don't forget, when we're looking for sines and tangents, the angle can only be in the right half of the unit circle. And don't forget also that when we label this unit circle, you have minus pi over 2 in the bottom and then pi over 2 in the top. So now I'm looking over here and I'm saying, what's the angle over here where the sine is 0? Where the sine is 0 at angle 0. So it's pretty straightforward. The answer should be 0. Now here's an inverse cosine. So I ask myself, what's the angle where the cosine is square root 3 over 2? Not for the cosine. So this is what we look at when we're doing inverse sine and inverse tangent. Right half of the circle. For cosine, it's a little simpler because the answer or the angle has to be in the top half, but the nice thing is the angles are 0 to pi like we're used to. So now I'm looking at the top half of the circle and I'm asking myself, what's the angle where the cosine is square root of 3 over 2? Well, that happens right there at pi over 6. Tangent, once again, tangent is this one up here. So I'm saying, what's the angle where the tangent is -1? Since tangent is sine over cosine, I'm looking for the angle where the sine and the cosine have the same value, although they have different plus and minus. And that happens down here in this fourth quadrant, because the cosine is square root of 2 over 2. The sine is negative square root of 2 over 2, so that's -1. Well, what's this angle here? This angle here is negative pi over 4. So 16, what's the angle where the sine is -1/2? Once again, looking in the right half, so what angle over here is the sine -1/2? It's actually right there, and that is negative pi over 6. Now, start with 17. We have what are called composite functions. So in class, we talked about, when we look at composite functions, the first thing we want to look at is to see if we can use the shortcut. Because the shortcut means that the trig functions cancel, and your answer is just whatever you start with. So this first problem, there's two kinds of problems. The first one's like this, where inside you have a number. And this is pretty simple. The sine, the inverse sine of 1/2. The only thing we care about is this number. Is it between that number between -1 and 1? If it is, we use a shortcut. If that number is not between -1 and 1, then there's no answer. It's not defined. Well, since 1/2 is between -1 and 1, we use a shortcut, and we just say it's 1/2. Here's another one, composite function, this time cosines. Here's my number inside. Now, you may not know right off the top of your head, so the question is square root of 3 over 2 between -1 and 1? You may not know for sure. If you need to, you can grab your calculator and decide what this number is as a decimal. And you do it, I think it's around 0.86, but it's definitely between -1 and 1, so therefore the shortcut works. So you just simply write down the number you start with. 19, sine of the inverse sine of 2, composite function. The numbers on the inside, will the shortcut work? Well, is that number between -1 and 1? In this case, it is not. So the shortcut doesn't work. And in this case, there's actually no answer. Undefined. Because if you think about it, basically you're saying, what's the angle where the sine is equal to 2? There aren't any angles where the sine is 2. The sine of any angle is always going to be between -1 and 1. Now we flip the script. So you notice these first three problems, the inverse trig function was on the inside, and you start with numbers, and we're just checking these numbers. Now the inverse sine of the sine, so the trig function on the inside, and now we have an angle in here. So we are going to now, first thing we're going to do is decide if the shortcut works for this. But in this case, what we check, we look at this angle, and we have to see if this angle is in what I call the allowed region. Now for inverse sines, the allowed region is the right half of the unit circle. And they also have to make sure that it has the correct label. So from -pi over 2 to pi over 2. So we look at this one. I'm looking at pi over 4. Is pi over 4 in the right half, or what I call the allowed region? Well, pi over 4 is right there. There's pi over 4. It is in the allowed region. If that's the case, then we can use the shortcut. And the answer is pi over 4. Here's another one, inverse sine of the sine of 3 pi over 4. So the question to see if we can use a shortcut is 3 pi over 4 in the allowed region. Well, where's 3 pi over 4? 3 pi over 4 is over here. So it's not in the region we want, so the shortcut does not work. So for this problem, and because this is a special angle, we're just going to work this out the long way, and you work for the inside out. So the first thing we ask ourselves is, what's the sine of 3 pi over 4? Well, the sine of 3 pi over 4 is square root of 2 over 2. So now this becomes a problem of the inverse sine of square root of 2 over 2. So now, since we're doing an inverse sine, we go back to the right half of the circle, and we say, what's the angle where the sine is square root of 2 over 2? And where is that? It's up here at pi over 4. So therefore, the answer to this is pi over 4. And you can see that this is why we can't use this shortcut. We started with 3 pi over 4, and the actual answer is pi over 4. Here's another one. Let's see if the shortcut will work. We have inverse cosine of the cosine, so we're talking cosines. Now we're looking at 2 pi over 3. Well, where's 2 pi over 3? 2 pi over 3 is right here. Looks like it's in the allowed region, the region where the inverse cosine is. So therefore, we can use the shortcut. Now the last one, another inverse cosine of the cosine. We start with an angle. Let's see if we can use the shortcut. Where is 6 pi over 5? Well, let's do this here. We're trying to see if 6 pi over 5 is in the top half of this unit circle. So we need to figure out where 6 pi over 5 is. Tricky thing is here, we've got denominator 5. Easiest thing to do is I'll go from 0, I'll change pi to 5 pi over 5. Well, hopefully it's obvious to you if I'm looking at 6 pi over 5, six pi over 5 is down here someplace. So therefore, since that angle is not in the what I call the allowed region, therefore the shortcut will not work. So now we have to figure out what this equals. Now, unlike 21, where 3 pi over 4 was not in the allowed region, but because this was a special angle, we were able to work this out inside out and got the answer. But down here, 6 pi over 5 is not a special angle. So now we have to use the principle of reference angles to find the answer to this problem. So for our angle, the question is, what's the reference angle? The reference angle, remember, is the shortest angle back to the x-axis. If this is 5 pi over 5 and this is 6 pi over 5, hopefully you can see that this reference angle is pi over 5. Now what's going to happen is we're going to use this reference angle to go ahead and come up with an answer that's in the top half of the unit circle. So we have two choices. Here's a reference angle of pi over 5. Here's reference angle pi. So this one is actually pi over 5. This one would be 4 pi over 5. So one of these two angles is going to be the answer. So which one should we use? Well, we look at the plus and the minus. This 6 pi over 5, the cosine here in quadrant 3 is negative. So which one of these two is also negative? Well, the 4 pi over 5 is also negative. So that's the one we choose. All right, so those are inverse trig functions. And that was the last problem in this review. There may be still a few other problems that might be on the test, but most of the problems on the test should have been somewhere in this review.